Hi, my name is Bauman Morafa, and I'm presenting metric-based measurements estimation for tracking in high clutter using Bayesian nonparametrics. This is a joint work with my colleagues at Arizona State University, and this paper is submitted to 2020 Asilomar Conference on Signals, Systems, and Computers. Oftentimes, when we receive measurements from the sensors, these measurements contain both measurements that are originated from an actual target and the measurements that are actually originated from false targets. These measurements are known as clutters. Clutters usually lower the performance of the tracker. So we have to be able to separate those from the actual measurements and then feed the actual measurements to the tracker to have an accurate estimate of the trajectory or the position or the velocity or whatever that's related to that specific target. Throughout this process, we're assuming we actually have a time-dependent number of measurements that includes both clutter and basically sensor measurements. These true measurements are assumed to be detected with some probability, and the number and the location of the clutter measurements are random. Therefore, to have an accurate tracking, all these tracking algorithms must basically incorporate all the measurements that are generated from the actual target. So we have to find a way to basically separate the clutter from the actual measurements. To formally state the problem basically follows a state transition equation that assumes a first order Markovity, and the relationship between the states at time k minus 1 is through some function f plus some noise. We also assume in the emission equation to be some relationship between the measurements that are generated from the actual target plus some noise. And if we have some measurements that are basically from the clutters, then we assume those are just z and k c. I would like to actually point out that if we could distinguish these two things, then if we actually had the actual measurements, then we could feed it to a Bayesian tracker, and then that would have given us a trajectory of that specific object. That posterior distribution that's given to us could actually give us a point estimate of basically the velocity, location, and pace of the object. However, the problem is we cannot separate the clutter and the actual measurements easily. So we actually have to have some method to be able to separate these two types of measurements to be able to have a better performance. Otherwise, the clutter measurements are deteriorating our performance. In the literature, there are two very famous methods to deal with clutters. One of these methods are nearest neighbor filters. These nearest neighbor filters are using measurements that are nearest to the predicted measurements to update a track. This can actually lead to a very poor performance of basically a tracker. They also assume that the object motion is actually linearly Gaussian. The problem with this method is that measurements that are chosen to update the tracker and basically to update the motion that we actually have, they might not even be related to the actual object. And that basically lowers the performance. Basically, they follow the philosophy of the winner takes it all. Another issue with this method is that the performance actually goes down as the probability of false alarm actually increases. Therefore, we have another method to deal with high clutter, which is called probability data association filter. These algorithms update the object state estimate using invalidated measurements and their respective posterior probability weighting. They assume the object motion to be linear, and they follow a Gaussian statistics. They also assume there is actually one measurement that are originated from the object, and the rest of the measurements are actually clutter. They also assume there is a uniform distribution in the space and a Poisson distribution in time for the clutters. There are several issues with this PDA filters, and there are a lot of like generalization of like these like methods. They're, for example, filtered gate structure methods, interactive multiple model PDAs, Viterbi, and fuzzy data like associations. However, all these models are suffering from a very high computational cost. So they're very computationally intensive. So we need to actually like have like a method that can actually do this thing for us very easily with a low cost. The way that we're proposing is that we're gonna like basically put a nonparametric prior over the space, and we're gonna estimate the measurements. Before we dive into that, I would like to talk about like Bayesian nonparametric modeling a little bit, and then dive into the problem. In general, Bayesian statistics uses like a probabilistic modeling to express any sort of like uncertainty and noise that we have in a system. And then we use inverse probability rule, known as Bayes' theorem, to basically infer the unknown quantities, basically to learn from the data and do predictions. Bayes' theorem basically states a posterior distribution is proportional to the likelihood times the prior distribution. However, in nonparametric setup, we're assuming the number of the parameters that we have is actually infinite. That is basically in contrast to like the parametric modeling. In parametric modeling, we're assuming the space of parameters is actually finite. So because of the fact that in nonparametric setting, we're assuming the space of parameters have infinite dimension, then Bayes' rule would not actually hold. These models are actually called undominated like models. So we actually need to like figure out how we can actually like do basically inference using the posterior distribution without actually using the Bayes' rule. The idea of like a Bayesian nonparametrics is that we use Bayesian statistics because of the simplicity of the frameworks. They usually give us like a very like nice framework. And we use actually like a nonparametric modeling because we want to actually like have like the complexity of like the world phenomena. Bayesian nonparametrics basically have found a lot of like different like applications. We have like a dependent Dirichlet process, infinite random trees, Dirichlet diffusion processes for basically priors for time varying detection of time varying number of the objects. We have basically like a hierarchical Dirichlet process as like a prior over the states and like over like number of the modes in maneuvering problem. We have like Dirichlet process as basically like a linear system, dynamic system, and like variety of like different things. Our approach to basically deal with clutter is that we're using like a very simple intuition that if you look at the joint distribution of the clutter and the actual measurements, we can actually expand this joint distribution as basically a conditional distribution times the probability of basically clutter. It is worth mentioning that given the clutter measurements, the probability of the measurements that are coming from target is actually independent from the measurement probabilities. That basically leads us to basically define a joint Dirichlet process over both of these probabilities. Therefore, we're going to define a hierarchical modeling that's basically describing our model. We're putting a Dirichlet process prior over the space of like parameters for the clutter. And given those parameters, we basically draw another Dirichlet process, another basically realization of a Dirichlet process. And given that, we basically draw the parameters for our actual measurements. And given these basically prior distributions, we can actually like form the likelihood. We can actually feed it to like a likely ratio test to actually make sure that like these measurements that are generated from like the target, and we use like those measurements that are generated from the target, and we feed it to like these like this like Bayesian tracker that basically comes from the fact that we had a prior distribution, which was a Dirichlet process, and the likelihood. As you can see, this posterior distribution is very complicated. This posterior distribution is not easy to sample from. So we actually need to have some sort of like way to sample from like this distribution. It is not easy, or it's not at all possible to actually analytically find this posterior distribution. So what we can do is we can actually basically propose a sequential Monte Carlo, or like a give sampling, to basically sample from like the posterior distribution. As soon as we have like these samplings, then we can actually like estimate whatever that's needed, and we basically can like have like the uncertainty over the model. This is basically our model in like one glance. The whole idea here is that we're actually like assuming a joint Dirichlet process. And based on that, we draw our data, and we basically feed it to like a ratio test to just make sure that we're getting like the measurements that are coming from the actual object. And given that, we basically find the Bayesian tracker. We actually like tested this method against a normal Bayesian filter. So we assume like we have like the whole data set, and we didn't like basically distinguish between the actual object, the actual measurements, and the measurements that are basically from the false target. And as you can see, the performance of like that algorithm, like by using only like Bayesian filter, this model has like a lot of like errors. So the MSE is actually like pretty high. We actually like computed the signal to clutter ratio, and the signal to clutter ratio was like 5.93 roughly. We also like tested our model against other filters. We basically tested against like a nearest neighbor, probably data association filter. And as you can see, the nearest neighbor filter that actually performs like very, very poorly. And the reason for it is that the measurements that are chosen to track and to update, they're not necessarily related to the object, to the actual target. So therefore, they actually like perform very, very poorly. And as you can see, like if we compare like the MSE for like these three models, the metric base, basically the method that's actually based on like a Dirichlet process, performs much, much, much better. So to conclude this talk, we basically proposed like an algorithm that uses a nonparametric modeling to basically estimates the measurements that are originated from the actual object, and basically like clutter. This model, as I mentioned, this model is based on like a joint Dirichlet process. We basically make no assumption about the prior knowledge about like the marginal PDFs. We incorporate like this idea to like a Bayesian tracker, and we basically estimate the trajectory. I would also like to mention this is not very difficult to like extend this problem to like multi-object tracking. We just need to like incorporate like this idea to like one of those like generalized methods to track multiple objects. For example, we can actually use like a dependent Dirichlet process prior over the states parameters, and then incorporate like this method to it, and we can actually like have a method based on like nonparametric modeling to first estimate the actual measurements and then use that to track multiple objects. This method is completely like probabilistic, so there is no optimization in this problem. And as mentioned before, this model does not have any like parametric assumption. Thank you for watching this, and I'm looking forward to talking to you more over this discussion.